Oh, I guess it's a bit early. Maybe 2 minutes. I wonder if this is being recorded. Anyway, let's check the old sharing. Okay. Oh, it's a bit thick. Maybe like this. Oops, Glen, what are you doing? There we go. I just wanted to make this like that. Yeah, it's fine.
Hey Glenn,
Jan,
how are you?
welcome. I'm good. How are you?
I'm good.
Thanks for coming.
Sure, you're welcome.
I'm just messing around.
Okay.
Um, I Yeah. I changed my annotation thing that I was using because yeah, in the first one of these seminars, I it just completely didn't work. And so I had to change it.
Okay.
Anyway, I'll stop sharing that. Okay.
Should we start?
Um,
Oh, wait a minute or
maybe we can start. I don't really want to take two more lectures. I would like to try to finish.
today?
Yeah, I'd like to try to finish my part today. And yeah, we'll see. If I miss out by 10 minutes or 15 minutes, it's okay. But I don't want to I don't want to drag my feet too much more. It's already my third lecture.
Yeah, it is. And then the seminar series on Willmore will continue
Yeah, then okay, so then after me, then so what I'm going to talk about today is finishing up Bryant's contribution, at least in this paper. I hope I'll do 10% justice to it or something. And
That's already a lot.
it's already a lot. This is one of the great mathematical papers of our time. And then I'll talk about the flow, which will be very, very brief because I'm going to come back into this seminar series much later and talk more about the details of the flow then. So I'll just very quickly talk about the flow. And then next up is Devesh, who's here. He's going to take on the formidable task of going through Leon Simon's existence proof for Willmore
Okay.
surfaces. And this is an extremely technical paper.
Yeah, I know.
So it may be 3 weeks or something until the next talk. We're going to see how we go. And then however many lectures that takes, then after that it will be parametric approach to Willmore
Yeah.
by
Approve regularity. Yeah.
the wonderful Jan. Yeah,
Yes.
that's right. And I don't know how long that'll take, but however long it takes, that's how much it
Prob-
is.
Probably a couple of times. Yeah.
And
Couple
then
of hours.
yeah, well, good, that's great. And then I'll come back and we want to finish off at Kuvert and Schetzler's Annals paper. Um,
Okay.
So if we have volunteers, actually, I don't need to come back. So if we have volunteers who want to take on the details of
You
the
mean
flow
the
stuff,
annals paper? You mean the paper on the point provability?
yeah, 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 that's right.
I can do that with my approach.
Yeah,
I
yeah,
don't
yeah,
know.
yeah.
Anyway,
Yeah, yeah. So there's two parts to that Annals paper. Yeah, okay. So what we can do, we don't do their removability result. We use your method to get removability, right? And
yes.
then we just do the flow part of their paper.
That well, yeah, okay, sounds good. All right.
Yeah.
Well, sorry everybody, we've started. What you have a sneak peek of what will happen in the next, I don't know, few months. So well, let's not waste any further time from the audience. Glenn, go ahead and continue on with Brian's paper, Willmore flow, etc.
Thank you, Jan. Thank you very much. Thanks everyone for coming. I am going to do my best to be understandable. Please, yeah, same disclaimer as last time. Be aware that I am very much an amateur when it comes to um, this kind of mathematics, this kind of paper. I mean, I am a geometric analyst, but my expertise is in flows, and this is definitely something I'm trying to learn. I've been trying to learn for a long time. Okay, so what I want to do today is continue where we left off. So what we had done is talk about this conformal Gauss map, this Y. And we can see that, so what it is it's the second congruence of mean curvature spheres on a surface. And what does it mean to be a second congruence? It basically means that you have these three equations, and of course the hat F, which is your Bryant dual, is does not project to the original F. So it's null, right? So this is the null condition. It has zero length, and it's orthogonal and tangential, right? So you've got this vanishing on y and vanishing on dy for the f hat. Now, looking at these conditions, that doesn't tell you anything about minimality. So what I wanted to do, which I found helpful when I was studying this, is give another interpretation of this setup, which is totally equivalent, that I feel is valuable. Okay, so this second interpretation is based around the mean curvature. And so let me just, I think I might have talked about this last time, but I'll talk about it again. So we've got an immersion F coming from mapping from sigma, it's a surface, into S3. It's conformal, and we fix a non-umbilic point in sigma. And then so that point that we fixed is P, and then for every Q that is not in the image of P via F, we take the stereographic projection, right? So this is the unwrapping of S3 into R3. And of course, you can do that except at one point, right? So we're going to, this exceptional point is going to be necessary. Of course, you need to remove a point before you can conformally transform S3 into R3. Or another way of saying it is you need to add a point if you want to project R3 back into S3. This is going to be important to keep in mind because, yeah, you'll see in the calculations. Okay, so we have these projections, and then we want to set the projection, right, of F via pi to be FQ, and this is centered at Q. Okay, so we're going to be varying this Q. And now I'm claiming that another interpretation of the Bryant dual is that you need to find a Q, right? So it's going to be realized via these stereographic projections. You find a Q such that the mean curvature of FQ, that's the projected one, is zero, right? So it's minimal. But also its derivative is zero, right? And so this is when you differentiate with respect to the Q. Okay, so this is really encapsulating your mean curvature sphere's congruence. Okay, another equivalent way of saying this is that if you Taylor expand the mean curvature, it vanishes to second order. Okay, and there's a unique point Q that satisfies this, and then that Q is going to be your Bryant dual, right? So for every P, you find a Q, you gather all those Qs together, and you've built your F hat, you've got your Bryant dual. Now, as a little preview, if there's only one such Q, right, if there's just one Q for every P, then the Bryant dual collapses down into a single point, which is a very important special case. Okay, I'm going to put my phone on silent, otherwise it's going to be beeping the whole time. Oh dear. Okay, so here we go. I'm going to be presenting this process as calculation, right? So we want to really calculate these. What does it mean for these identities to be satisfied? And if we go back here, we see that we're taking a conformal change. And so we're going to start really from scratch. As a conformal map, we can work out the change in the metric, right? We use this conformal factor. And the UQ here, you can calculate this from the definition of stereographic projection is this log. Okay, and now, okay, we've already said that HQ is the Euclidean mean curvature of FQ. And then another good exercise is to work out how does mean curvature transform via conformal transformation. And you get this equation, right? So for HQ, you've got the e to the minus UQ. This is your conformal factor. You've got the original mean curvature, and then you have this normal derivative term. Okay, this is your extra term that you get from the ambient geometry. Okay, now what we're going to do is calculate the normal derivative of this UQ. You can just calculate it from this logarithm definition here. This is just a simple chain rule. I'm sure everybody can do it. You get this quotient, and then I just plug this into the previous equation, which was H minus D nu UQ, and I get this term in the middle. Now, this term in the middle, I want to save myself some typing. I'm going to call this FQ, right? And the claim is that the vanishing of H to second order is equivalent to the vanishing of F to second order. So we can just immediately ignore this conformal factor at the front. This is just a calculus fact. You can see it by differentiating both directions, which, yeah, you just calculate it and you plug in, you can get both these implications. The multiplication doesn't cause any trouble. It all works out fine. So we're going to focus on this quantity F. I'm not sure if this has, oh yeah, it does have geometric interpretation. Okay, so now we've got to really get into the calculation. I'm going to decompose Q, right? This is a point in S3 into three components. So we've got the component that is in the direction of F, right? So we've got a coefficient here, which is just the inner product. Then we've got the tangential component, right? The tangential component itself has a magnitude. This is not a unit vector. This is literally just the tangential projection of Q. So it's two-dimensional because S3, okay, so in this frame, you would have four vectors because S3 is inside R4 in the setting. So the T is just some remaining piece. And then the beta nu, this is your normal piece. Okay, and now I'm just setting this D for denominator. This is 1 minus FQ. This was on the bottom of this fraction. Okay, and so then if F vanishes, then that's exactly the same as H minus beta over D vanishing, which is beta is HD. Okay, H mean curvature, and then D is this deficit denominator, whatever you want to call it, which is 1 minus alpha. All right, nothing's happened. But what we can already see is that if we know the mean curvature, if we know the radial part, then the normal part is already forced. Okay. Yeah, and I already said this mean curvature 0 is minimal. Okay, so that's F being 0. What about DF? Okay, so we differentiate. We need to apply vector field X to this ratio and use quotient rule or the chain rule and then add them together as you wish, you get this formula. I think it's pretty straightforward to see. So you've got Gauss-Weingarten here in this equation. And you differentiate through the top here, you differentiate here, you get the A. You differentiate the F, you get X. You get T, sorry, you get XT. And then, of course, you've got this factor at the front as a product. I think it's pretty straightforward, hopefully. And now the zero condition, so on F, gives you this relation, so we just noted a second ago. And so you get already something really profound. Okay, so this is the first part of the talk where I'll slow down. Why am I slowing down? So here we have something very special. I'm sure people who've seen this before immediately know what this is, but maybe everybody can see it straight away. But this object just came up from our calculations. We were just calculating blindly, and I've just factorized this expression at the top here, and I've found this object. This, of course, is, well, I guess minus, the trace-free second fundamental form. Okay, so here we've got immediately the presence of umbilics causing a big problem, but we're already assuming in the beginning that we're away from umbilics. But here you see you've got it right in your operator. Okay, so yeah, I'm just summarizing here. If df is 0, then you've got x applied to gradient h equal to this operator applied to x, which we can, of course, invert if it's invertible, and we get the tangential component as fully constrained. Okay, so now on this slide, I'm just revealing why this is, in fact, the trace-free second fundamental form and why this operator is invertible away from umbilics, because, I mean, you can just calculate it in a basis and you get a nice basis, and you get exactly the 2x2 expression for the trace-free second fundamental form. And you can see, right, that eigenvalues are going to not be 0 unless you're an umbilic. Okay, so now we've really fully constrained our original point Q. Okay, so you might remember our Q, it was alpha F plus T plus beta F with nu. Beta nu, Glen, can you just not say the wrong thing? Beta nu. And so you write, and then of course you know that Q squared has to be 1. So we can square this orthogonal decomposition, and we get this expression here on the right-hand side. Oops. Draw a straight line, please. Okay. And this expression on the right-hand side factorizes. It factorizes into d times a bracket equals 0. And d equals 0 would give q equals f of p, which we remember is illegal, right? So this all the way back up here, from the very beginning of our calculation, we had q not equal to f of p. So we reject d equals 0. D is not allowed to be 0. And so the bracket must be 0. Okay, well, the bracket is basically d times this denominator minus 2. So bracket being 0 gives you this expression here. And so you get this explicit formula now for the Bryant dual at a point P. It's given by this expression. Of course, it's a little bit, I mean, it's quite nice as a formula, and I think it's quite satisfying to have a formula for the Bryant dual. But there is this sort of inverse operator thing applied to gradient H, which you may not like. And the D, of course, is just, yeah, I have a thing with notation. I'm sorry, people, but but at least I put it on the slide. Okay. You can think of the D as the normalizing factor. Okay. So we've constructed our F hat. Um, and here I'm just recasting it, trying to give you some meaning for this formula. Um, it basically follows the old breakdown that we had. Oh, did I write alpha F? Yeah, I did write alpha F. So here we've got alpha F, and then this is your T, and then this is your beta nu. Okay. And where did all these pieces come from? This is really just a summary. We've seen it already. Okay. And this formula is all if and only if, right? So this defining f hat by this formula ensures that the mean curvature vanishes to second order. Right. So that that's a very satisfying result. But it's difficult, I guess, at least for me, when I first saw this to intuitively appreciate that it is equivalent to the Lorentzian picture, right? So we've now seen two different constructions for Bryant dual. One very geometric, very also satisfying, very elegant, where you sort of you reflect across a null. You have this light cone in the tangent planes, and one direction gives you the original immersion, and then the second direction gives you the Bryant dual. It's very satisfying as well. And of course, we built that from the mean curvature sphere congruence. So they both come from the same thing. So it's not really unexpected that they're equivalent, but to me, at least, for my brain, I see Lorentzian, light cone, whatever, and I think, okay, that's one construction. And then I see this very explicit vanishing mean curvature, vanishing derivative of mean curvature. And I think that must be, then why does that have to be the same? But it is. It is. Okay. So that's just recapping the construction. Right. So you get these two equivalent ways of describing f hat at P. And I think that's pretty awesome. So I guess what I'm saying is I kind of like the second one. The second one makes more sense to me. It's more constructive, at least from my perspective, but the first one is more beautiful. So I present both for you. Okay. So now so I had some good discussion after the previous lecture with some of my students, and I'm really happy actually that there is interest and discussion after the talks. So very happy for that to happen. And a few of those discussions centered on the question of, but do you really need the Willmore equation? What does it do for you? And that's the purpose of this slide. So if you have any arbitrary immersion, well, within reason, you do get this second null line, all right? At least as long as you're away from umbilicus. So you can define some kind of a Bryant dual, but it doesn't need to be good. It can be crazy. And so what the Willmore equation lets you conclude is that if the original immersion is Willmore, then the conformal Gauss map Y is minimal. Okay. And for the F hat, you get a conformal map, but it can be branched. Okay, so this is the really the first part of the story. So you have the construction of the Bryant dual that gives you another object associated to your immersion, and it can be constructed for any immersion. It may be a terrible object, but you can still define it in some way, in an appropriate way. And now you add hypothesis, right? So you add Willmore to your immersion, to your space object, and now your Bryant dual becomes, uh, well, your conformal Gauss map becomes minimal. It can be branched, of course. Branched, by the way, means that the metric is degenerate. Okay, so it doesn't mean it's necessarily um, discontinuous or something terrible. But it may not be smooth. It may be, for example, okay, and this will come up later, so I'll talk a little bit about it. I wish I had a blank piece of. Can I have a blank? Can I please have? Okay, I've got some space here. So I'm going to draw a very simple picture. I'm going to take my favorite minimal surface, which is this one. And it's going to look like that. Okay, so this is, people probably recognize this. It's a catenoid. And I'm not going to draw it very well, I'm sorry. Okay, now I've drawn a catenoid that's been scaled. So there are many catenoids. I've drawn one that's scaled so that it is tangential to a unit. Oh, Glen. A unit. Can I make this less? Oh, oh, that's not the worst drawing ever. So it's tangential to the unit sphere, centered at the origin. And now what I'm going to do is choose another color if I can. So please, may I have something else like pink? Oh, I do love pink. Okay. And so, okay. And so now what I'm going to do is I'm going to send every point on the catenoid, P, I'm going to send P to P over P squared. This is called inversion. Okay, and it's a conformal map. And it's going to take this entire catenoid and put it inside the sphere, centered at the origin, right? And so this circle on the equator of the sphere is not going to move. But all this material that's outside, so maybe I should draw some more material, but all this stuff that's out here is going to be shoved inside the sphere. And what's it going to look like? Well, of course, I wouldn't have started this discussion if I didn't already know the answer. But it will look, okay, I'm going to draw it down here because I need more space. Okay, so it's going to be tangential to the sphere, and it's going to increase in height from the horizontal plane to a point where it will reach a maximum. And now I'm going to need to draw some kind of origin. And then as the point becomes further out to infinity, we're going to be slowing down, right? So the growth of a catenoid as it goes out to infinity is quite slow. And so when we divide by the magnitude squared, we're going to be dividing by something which is much bigger, and it's going to drop down to the origin like this. Now I've drawn this picture very badly, so I'm sorry to all my inverted catenoid loving friends. I've butchered this one, but that's okay. So this thing is this is your inverted catenoid. And here at the origin, if you write this as a graph, right? If you think of this pink profile, we write this curve as a graph. It's not smooth. It's not C2. Okay. And um, and that's branched. Okay, so that's a branch point. It's an example of a branch point. All right, let's continue. That's the purpose of that discussion, was just to give an example of a branch point. I know that there are other reasons to talk about that, but that's all I wanted to say for that. Okay. Okay. So, right. Let's keep developing our theory. Umbilics make a priori a problem for Bryant's constructions. Um, and so it's a big job for him to deal with umbilics, extend the surface through umbilics, which is a type of removability result, in general, to understand what's happening around umbilic points. And probably one of his really main technical contributions is that you can extend through umbilic points, which is not clear. It's not clear that you could do that, and it's not true that you could do that for an arbitrary motion. Okay. One of his, I guess this is just due to him, but one of his main tools that he works with is called the Bryant quartic. Okay, now I don't want to spend too long on this one, but the quartic is fundamental. Okay, it's defined like this, QB for Bryant. Okay, it's just the inner product of, complex coordinates, YZZ with YZZ, and it's quartic. So this is DZ with itself 4 times. Now, you probably don't remember, but there are quite a few different orthogonality relations that we have between YZ and YZZ and so on. And using those, you can work out if you have a change of coordinates. So that's what's going on here, change of coordinates. Okay, so W is your new coordinate and your old one is Z. And you just calculate what this is in the new coordinates. You get a nice transformation law. And so this really does define a quartic differential form. Okay, and I've just recorded down here for the people who know about these things. If you haven't seen canonical bundles, don't worry. It's not, we only need one small fact from that theory, and we're going to use it as a black box. If people are interested in learning about canonical bundles, then that's fine. We can talk about that as well. Okay, so it's a quartic differential. I haven't shown why it's holomorphic though. Holomorphic quartic differentials are very constrained, and that's why it's important to see that it is holomorphic. To check that it's holomorphic, we just calculate, right? So we differentiate with respect to the conjugate of z, z bar, this factor in front of the dz to the 4. We get this formula here, which is very obvious from the product rule. Okay, and then we have this minimality equation for the conformal Gauss map, which we can differentiate to give us this equation. And I haven't bothered to evaluate this bracket because we don't need it. What we can do is simply take the inner product with YZZ, and then YZZ with Y is annihilated, and YZZ with Y, oops, not that one, Glen, with YZ is annihilated. Okay. No, Glen. Okay, so YZZ with Y and YZZ with YZ, they're zero, and so you get DZ bar being zero. And so it's holomorphic. And so that's your next kind of piece of the puzzle. So we've constructed Bryant dual, and then we've observed that if you're Willmore, then Y is minimal. Now we've observed that if you're Willmore, then Bryant's quartic is holomorphic. So it's a quartic differential form and it's holomorphic. Okay. And now we get to the first big result. Okay. So here we go. We're going to have F as our immersion. It's connected, it's Willmore, and it's not totally umbilic, so it's not a sphere. Okay, and now the first statement of this theorem is that the Bryant dual extends across the umbilic set in a smooth way. Okay, so that's the first statement. The second one is that if, okay, so if the Bryant quartic disappears, is zero, is trivial, then F hat is constant. And so that was that case that I was telling you about. If the same Q works for all the P, then the conformal transform collapses to a single point. Okay, and so that is exactly what happens when Bryant's quartic disappears. Okay. Now, on the other hand, if Bryant's quartic does not disappear, then we actually generate more Willmore immersions, right? The Bryant dual is conformal branched Willmore immersion. That's the first statement of the second part. And then we have this, reflexivity relationship. We can take the dual of the dual and we get back to the original F. Okay, so you can't generate, sequences of conformal branched Willmore immersions using Bryant's duality theorem, but you can generate a second one, right? So this is very much like Weierstrass representation for minimal surfaces. You can, to every Willmore immersion that's not totally umbilic in S3, you can associate a second one. Or the dual is constant, right? So you either have the dual collapsing to a point, and then you can't take the dual of a single point. That doesn't make sense. It's not an immersion. Or it goes to another Willmore immersion, and then if you do it again to that one, then you get back to where you started. Okay, so I think, this is just a really beautiful result, and has very dramatic application, which we're going to talk about now. Okay, so Bryant's holomorphic differential vanishes if sigma is 2D sphere. Okay, so I don't want to go too deep into this. I did dig a little bit because Bryant's justification is that, it's well known that if you have a holomorphic quartic differential on S2, it must vanish. But I am not aware of that. So, this just shows my lack of education in general. But I convinced myself it was true by doing some calculations. If I think of S2 as CP1 and I use Z to create a quartic differential form, then I can convince myself that because of the Liouville theorem, if it's holomorphic, so you have a Liouville theorem for holomorphic functions, holomorphic forms, you have a Liouville theorem, um, then, okay, so it would have to be smooth, which means that you would need Q to be decaying very quickly. But then if it's decaying very quickly, it's bounded, and so then Liouville gives zero. Okay, so at least that's maybe this is like a very barbaric way of seeing it. It's like perhaps totally repugnant to anyone in geometry. I'm so sorry if that is you. But that, at least for me, this is how I understand Bryant's quartic differential form vanishing. um, anyway, it does vanish, and that means that we are in this. Just a second, I have to. Sorry about that. Okay, so where were we? So now, if we are in S2, let's use pink. I love pink. So if sigma is S2, then QB is 0. And so we're in the first alternative of this result, which means that Bryant dual is constant. Okay, and so what does that mean? Now we're in a situation where we've used some kind of deep topological result to learn something about Bryant dual, but what does that mean? And now this really goes into another deep section of this paper, okay, which goes like this. So we have one possibility, right? So there's one possibility, which is case one. We assumed before that F was not totally umbilic. So it could be totally umbilic. If it's totally umbilic, then we have a round sphere. That's the only possibility. And its Willmore energy is 4 pi. Okay, so that's already one possibility. The other possibility is that it's not totally umbilic. And then because we're on S2, the quartic differential, holomorphic quartic differential must vanish, which means that Bryant dual is constant. And then we start to work some more things out. Then, because of what we saw before, because of the characterization of the Bryant dual as being the map that the conformal map that sends your original immersion to something with vanishing mean curvature and the derivative as well, but we just need the first one, then stereographic projection from this single point turns your original immersion into a complete minimal surface. Okay, and the complete minimal surface I'm claiming, or Bryant proves, has finite total curvature. That's not too difficult to prove, but it also has embedded planar ends. Okay. Now, what does this mean? Well, what it means is that what it means is that I'm going to explain it, but basically the logarithmic terms in the residual calculation vanish. But let's connect this with an earlier thing that I talked about at this point. So one of the earlier things I talked about was this picture. Okay, it's inverted catenoid. So here I've done the construction in reverse. So I've started with something in R3 and I've inverted it into S3. Okay, but imagine in this discussion here, we're going the other way, right? So maybe I'll draw it down here. Okay. So if we're starting off with something in S3, okay, so imagine we have an inverted catenoid in S3, and then we uh, project that to R3, we might think we could see a catenoid. So we could say that a catenoid is a possibility. But spoiler alert, this cannot happen. Oh, this does not happen. Why? Why does this not happen? Well, I mean, this is not a proof. This is just a simple example. But remember that this object is not smooth. This is not C2. And this comes up later in Bryant's paper, but this fact that we assumed that this original immersion here is a smooth object, and we're starting in S3, right? So we're not, so in Bryant's perspective, we start in S3 and we end up in R3. Now, a lot of the stuff that I've done, we start in R3, and then we see that S3 is something that we can go into. We don't start there. But here we're starting in S3. And so we're assuming regularity in S3. And that assumption is absolutely necessary for this characterization, which, because a lot of people start in R3, they might not really understand, it might seem like, oh, you don't know if you're smooth in S3, but we're assuming that. That's a big assumption. Okay. And so basically what this assumption lets you do is rest on a big, machine that's, I think, primarily due to Osserman on minimal surfaces with different types of ends. And so I'm not going to go into that, but again, it would be a beautiful topic, but I'm just going to use it like a black box. Okay. So, all right. So I'm going to skip this slide because I've already talked about why why the projection is minimal. Okay, I've already talked about this. I've already talked about this. Okay. Yeah, so Bryant numbers his theorems A, B, C, D, blah, blah, blah. And his theorem E is is this one. You get a complete minimal immersion with finite total curvature. Okay. This set D, right? So is the set of punctures that gives you all the ends, right? So whatever you map into your D, right, into your Q, that's where all your ends have been packed into that point, right? So in this setting, if you imagine again the inverted catenoid, the ends get packed into the origin, right? So you've got multiple ends, you've got and they're collapsing in on this point, and so that's denoted here by this D. Now, if you only have one end, then you're actually inverting a plane, and you're going to get a round sphere. That's important later. Okay, I've got this terminology here, and this is something that you would have to prove that the ends are embedded, and they have something called zero logarithmic growth. This means that the log term in the residue disappears. Okay. So why they complete? The completeness is an explicit calculation. You can calculate how the distance it changes by stereographic projection, and so you can see that if you take a path that approaches P, then this distance goes to zero, and you are going to get infinite length, which implies completeness of the ends. It's not surprising. Why do you have finite total curvature? This one is pretty straightforward. You use algebra to express the second fundamental form in terms of A0 and the mean curvature, but of course the mean curvature vanishes. And so you get that because the Willmore energy And because A0 squared d mu is conformal invariant and it's finite on the S3, then it's finite in the Euclidean space as well. This finite total curvature is required for Osserman's machine to start to work. Okay, now this is incredibly brief, but how do we see this residue? Well, yeah. We write down the coordinate one forms of minimal immersion, um, and we know from Osserman that they extend meromorphically, and the x, which is your end, can be written as the real part of the integral. Okay, and now you expand them out and you integrate. So you know that from the theory that you have something like 1 over z squared, or it's like minus a over z squared. And then you've got b over z and blah, blah, blah. And so you integrate this up. This turns into a 1 over z, which is fine. That's going to be smooth. So once you invert, that's going to be smooth. But this one is your logarithmic growth. That's going to turn into a log when you integrate. And when you invert, this thing is going to be C1, but not C2. Okay. This is exactly like our catenoid. All right. So we don't want this. And we basically we're not proving that it doesn't happen because it can happen. It's that we're assuming it does not happen, right? So if the log term was there, then an explicit calculation, you can just calculate what happens when you invert an end with this form. You get C1 but not C2. It's an explicit calculation. And so it can't in particular be smooth, and so we assumed that it didn't happen. There's not really anything happened. It's not a very satisfying proof because it's not a proof, but we assumed it's not true, so it's not true. And now, I'll write this name down, Osserman's machine, we conclude that the end must be planar. Okay. And then, of course, the catenoid is your counterexample. If we don't assume that the original immersion is smooth, then you can have catenoidal ends. Okay, great. So we've understood quite well what the stereographic projection of our surface is once we are in S2. So if we're in the S2 situation, then we know the Bryant dual turns into a point. We know that we can construct this minimal surface with finitely many ends. We know that it has finite total curvature. We know that the ends are planar. Okay, so what? Not planar. We know that the ends they're not logarithmic. They have zero logarithmic growth. I think you could also call them planar ends. A locally embedded. Yeah, I'm not sure if the terminology planar end is accurate there, but at least zero logarithmic growth is. Okay. So how do we continue from here? Well, Bryant does not stop there because, I mean, there's a very dramatic application of this result now, right? So now I'm going to look at the problem where you start in R3, right? So you start with a complete minimal immersion. It's a map from S2, take out finitely many points into R3. It's got finite total curvature and, okay, yeah, embedded planar end, so zero logarithmic growth. Okay, now you invert, and by all of our work, you get a possibly branched Willmore sphere in S3, right? So you can also go backwards. And this is, I think, at least for me, this is the more familiar setup. But it shows that you can go forwards and backwards. And you can also show, using the fact that these are planar ends, that each end contributes a specific amount of energy to the Willmore energy of the surface. And so you can already see that, well, I call this D later, but anyway, you're going to get this magic 4 pi m quantization phenomenon for the Willmore energy, right? So we automatically find that, okay, we've got these possible candidates for values. We haven't actually demonstrated that they exist, but these are our only candidates. Now, we did see already that 4 pi does exist, and that's a sphere. Okay, but then there's a huge gap. So you start off at 4 pi, and there's nothing until you get to at least 8 pi, right? So if you're Willmore and you're not totally umbilic, then you've definitely got. So we get two pieces of information. We get that the number of ends is at least two, and that the Willmore energy has to be bigger than or equal to 8 pi, which is the main application actually of this entire thing to the flow. Well, the the part of the flow that we're going to talk about. You can apply this in other ways to the analysis of the flow, but we haven't. We're not. Maybe we'll talk about those later. But there's at least in the plan. This is the main application. Okay, so here's a summary. I've been talking about this already, so I might skip this slide, but this brings things together, right? So you've got, yeah, maybe I will skip it, but I've already said most of this. And just to reiterate, Willmore less than 8 pi, we have a round sphere. Okay, now I've got 5 minutes left, and I'm going to very, very quickly. Oh, I don't know. Oh. No, I'm going to use a little bit of Devesh's time. I think I'll just end a little bit earlier and ask if there are any questions, and then I will just use a little bit of time in 2 weeks to go through these few remaining slides. So yeah, thank you for your attention, everyone.
Thank you, Glenn. Thank you very much for really an incredible job in synthesizing a very, very difficult paper. Very
It's okay.
profound,
I did okay.
very profound work, actually, and you did a remarkable job. Really, I hope the audience enjoyed. Are there any questions? You get a lot of claps.
Yeah, thank you guys. Thank you guys. Thank you very much.
Okay, no questions. I have one question. It's more of it's more curiosity for myself. So I know, of course, you presented very well Bryant's construction of the dual map and this Lorentzian picture or the anti-de Sitter picture that Bryant uses, and then you showed us also earlier today a bunch of calculations that were. Are they original? Are they from you, or did you get them somewhere? Or
Um, I've seen those I've seen them before when I was in Germany.
okay,
So they were deposited in my brain 14 years ago.
okay,
So actually, at Magdeburg, I shared an office with Anna Delacroix, and we had a
I
really nice,
remember.
yeah, a really nice group there, led by Hans Christoph Gruner.
Yeah.
And Bryant's paper was one of our, papers that we wanted to go through, along with Rivier's paper for the seminar. And I think I don't remember exactly who it was. It could have been Anna herself who needed to present the construction of the Bryant dual. And I think that she might have been the one to show me that you can do this calculation.
Yeah, so
Um,
it's nice because it's very explicit, or it's a bit messy,
Well,
but
I have my typical notation problem. So my
no,
students
but
will testify that I keep changing notation every 5 seconds.
no, but to geometers, this would be a horrible way to approach the question, right? Geometers would say, absolutely don't do what you're trying to do. Just stay in this anti-de Sitter package, which kind of does it all for you into one complicated construct. And so, but doing it explicitly, like using calculus, basically,
I
is
just did the product rule and the chain rule.
no, but it's very revealing. Actually, I think it's a good approach to for someone who doesn't have a geometrical mind necessarily, someone who's more like around analysis, I think gets just as much of an intuition from that computation as from the abstract construct of Robert Bryant.
Yeah, thank you. Thank you for saying. That's why I wanted to present them both because you can't not present the anti-de Sitter construction. You have to present that because that's what's in the paper.
That's right.
But this other one, also, I had an ulterior motive because you and I were talking about generalizing this to other things, and the anti-de Sitter to generalizing that seems quite tricky and maybe impossible. But maybe generalizing this vanishing mean curvature and so vanishing mean curvature to second order, maybe, or maybe you need to take fourth order or something for a four manifold. I don't know, but maybe
I don't
that
know.
could
Yeah, yeah.
be there could be something.
Four manifolds to me, it remains a big mystery, even in codimension. Well, Brian's construction in dimension two that you presented, it is a purely codimensional one construction. In fact, as we said last time already, it does not work. If you try to actually extend it to higher codimension, and if you try the computation, you see why you hit a roadblock if you're not in codimension one. And in dimension four, even in codimension one, as far as I know, there is no good. Dorian Martineau has published a result around that, but it's not very convincing. It's not, in my opinion, it's very contrived, and it's not the natural energy that one should look into in 4D. Anyway, let's not get into that too much. So, thank you, Glenn, again. Thank you very much for taking the time to do this. And it was really worth the excursion, the 10-minute excursion in the computation, I think. So, next time, I guess you'll take a few more minutes and
Yeah, 15 minutes maybe, and then I'll hand over to Devesh. Probably be in about 3 weeks, I think.
okay, very good. Then we'll see you then. We'll see everybody then. And I guess we're disbanded for now.
Yeah. Thank you, Jan. Thank you, everyone, for coming.
You're welcome. Cheers.